Hello, everyone. Thank you for coming to our session on the Data Protection Working Group. My name is Xin Yang. I work at VML by Broadcom. I'm also co-chair of Kubernetes 6 Storage and the Data Protection Working Group, working with Dave.
Hi, I'm Dave Smith-Uchida. I work at Veeam on our Kubernetes backup products.
Here's our agenda today. We will give an update on what we did in this working group, who are involved, the motivation for establishing this working group, and some projects we're working on, and a white paper that we're working on, and finally, how to get involved. We wrote a white paper a while ago on the data protection workflows in Kubernetes. Here are also some links to our previous talks at KubeCons. Here are some companies that are supporting this data protection working group listed here. In Kubernetes, day one operations for stateful workloads are well supported. We have persistent volumes and persistent volume claims to support the volume operations. We have workload APIs such as deployment and stateful set to manage the workload. And more stateful workloads are moving to Kubernetes. These workloads moving to Kubernetes to take advantage Kubernetes self-healing ability, agile deployment, the built-in scalability, and portability. On the other hand, day two operations, such as data protection, are still limited. GitOps workflow has limitations on the support for stateful workloads. Secrets, config maps, and data stored in persistent volumes are not on the Git. So we need to have a better way to support data protection in Kubernetes. That's why we formed this working group. This working group is sponsored by both 6 Storage and SIGApps. This figure shows the backup workflow with existing and missing building blocks in Kubernetes. The blue color shows the process. The green color shows existing Kubernetes components. Yellow means work in progress, and orange means missing Kubernetes components. To back up an application in Kubernetes, we need to back up 2 pieces of data. We need to back up Kubernetes metadata, and we need to back up the data stored in persistent volumes. For the volume backup, there are 2 approaches. We can either use the native data dump, such as MySQL dump, or we could use controller-coordinated approach to take a volume snapshot. To ensure application consistency, we need to quiesce the application before taking the snapshot and unquiesce afterwards. Both the Kubernetes metadata and volume data needs to be exported to a backup repository. A backup repository is a location or repo to store your data and metadata. And here we have a few green color components. They are existing components in Kubernetes. There is a application CRD owned by SIGApps. We have volume snapshot owned by 6 Storage. We have volume mode conversion that prevents unauthorized volume mode conversion between a file system mode and raw block mode when you create a PVC from a volume snapshot. That features GA in 1.30 release. We have consistent group snapshot that allows you to create a group snapshot, crash consistent group snapshot of multiple volumes at the same point in time to ensure right order consistency. And this feature moved to V1 Beta 2 in 1.34 release. We have Cozy Container Object Storage Interface that defines Kubernetes APIs that allows you to provision object buckets, just like how a PVC is provisioned. And this feature is targeting V1 Alpha 2. We also have change block tracking. That's a feature introduced in 1.33 release. I will talk more about that later. This figure shows the restore workflow with existing and missing building blocks in Kubernetes. To restore an application, we first need to import the backup from the backup repository. We need to import the Kubernetes metadata. We need to restore them. We also need to restore PVC and PV. If the data volume was backed up natively, we need to restore from the native data dump. Otherwise, we need to rehydrate the PVC from volume snapshot or volume backup. We have a volume populator here. That's a feature moved to GA in 1.33 release that allows you to create a PVC for an external data source, such as a backup, not just a volume snapshot or another PVC. Now let me do a deep dive of the change block tracking feature. We introduced APIs to support change block tracking in Kubernetes. This API allows you to identify change blocks between two snapshots of the same persistent volume. This allows the backup application to support incremental volume backup. It also decouples the backup system from the storage system. A backup application can call this common API to retrieve the snapshot metadata instead of calling vendor-specific APIs directly. To support CBT, we added a snapshot metadata service in the CSI spec and added 2 new CSI RPCs. We have get metadata allocated that retrieves metadata for allocated blocks for a single snapshot. We have get metadata delta that retrieves metadata of change blocks between 2 snapshots of the same volume. And this support is for block volume only. We also added 2 Kubernetes snapshot metadata gRPC RPCs. And a backup application can call this gRPC RPC to retrieve snapshot metadata. We have a snapshot metadata sidecar that implemented those new gRPC RPCs. We do have a new CRD, a snapshot metadata service, that contains information on how to connect to the gRPC service. A CSI driver creates a CR, and a backup application retrieves that CR and uses that information to communicate with the gRPC service. This shows how CBT works. A backup application obtains an access token from the API server. It uses that token to call the snapshot metadata service to retrieve the snapshot metadata. And the snapshot metadata service verifies the token with the API server. It then obtains the snapshot ID from the volume snapshot. Then the snapshot metadata sidecar calls the CSI driver using that snapshot ID to get the snapshot metadata. After that, backup application can create a PVC from the volume snapshot, attach that PVC to a data move pod, and read blocks from it. We recently made a change in the get metadata delta API. Originally, this API requires the names of 2 volume snapshots. That means the base snapshot may need to be retained for a long time. Requiring long-term retention of snapshot can cause performance degradation on some storage systems. And that means it defeats the purpose of supporting CBT, which is for efficient backups. To solve this problem, we changed the base snapshot name to base snapshot ID. This way, we no longer require the base snapshot to be retained. There is no CSS spec changes, no RBAC changes. This project is currently alpha since the Kubernetes 1.33 release. We have active participation from the backup vendors and storage vendors. And the next step is to work on moving this feature to beta. Now let me hand it over to you, Dave, who will talk about the white paper.
Thanks, Xing. So we had done, we had done our first white paper on basically the need for data protection in Kubernetes and what kind of support in Kubernetes we need for that. So we actually now have the building blocks for doing data protection. So we thought it would be good to put together a white paper on best practices for data protection. So part of that is understanding the resiliency needs of your application, picking the right strategy, and then sometimes you may actually need to make modifications to your application. So the white paper is under construction. I'm going to give you a preview of some of the stuff that's in it, and contributors and reviewers are needed and very welcome. So, if you have anything that relates to data protection, come take a look. So for data protection, there's a couple of industry standard terms. There's RTO, which is the recovery time objective, and that's how long it's going to take to get the system back up and running after a disaster. And then you've got an RPO, which is your recovery point objective, which is how much data you might lose after recovering from a disaster. So ideally, both of these would be 0, but there's costs associated with them, both in terms of running costs and costs involved in making your application work with some of these strategies. So when you start planning out your data protection strategy, you have to see the impact of data protection, what kind of performance hits your application may take, how much engineering you might have to do in order to get to your required RTO and RPO objectives, and then you have to look at your costs, things like storage, network, compute, etc. So some of these strategies we lay out here and what the impact's going to be. So you may say, look, my application's completely stateless. There's everything I can redeploy from GitOps and we'll be good. And that's perfectly reasonable. If that is actually the way it works, then that's fine. Your RTO is going to be the time to reinstall the app. Your RPO is 0 because you don't have any data that needs to be restored. And it's a low impact on your app since your app should be able to be installed and your cost is low. However, once you start adding stateful data into your cluster, and that may be either stored in PVCs, it could be in resources that get created that aren't reflected in GitOps. Your application may be storing some of its state in resources. So then you have to get into a more sophisticated data protection strategy. So backup and restore is pretty well understood. Your RTO is going to be a medium. You have to restore the data, possibly just restore snapshots, and you have to bring the application back up from the restored resources. Your RPO, again, is going to be kind of medium. It depends on how often you're doing backups and how much data is being backed up. And then your app impact, it's going to depend on the consistency strategy, and I have a slide on consistency strategies in a bit. And then your cost, it varies, but it's usually, I'd call it a medium cost because it's really related to how much data you're backing up and protecting. Replication is really nice if you can get it. So one strategy is to do replication with a cold copy. So you have like an application running in one data center or region, and then you have a cold copy of it that's being replicated. For example, you might be replicating the storage across the clusters, but the other application isn't up and running. So your RTO should be low because it's just the time to bring your application up. Your RPO, if you're doing asynchronous copies where the data is written to your primary cluster and then it's echoed over to the secondary, but not necessarily immediately, your RPO can be low. If you actually do synchronous copies where every write in your primary cluster has to complete in the secondary cluster before the application acknowledges that the write's completed, then your RPO can actually be 0. But you will have some impact. So async, most storage systems can do this, databases can do this, and it's not a big impact on the performance of your application. If the storage system or database is actually waiting for the remote side to complete before your app continues on, your performance impact may be higher, and things like network outages may give you more headaches. Your cost is going to be higher than backup because you're going to need to have your data in hot storage, not object storage. And you probably need a fair amount of bandwidth. And then, excuse me, the last option here is replication with a hot copy. So you may have your application distributed across multiple data centers. You're able to fail over between data centers, or you may always be running in multiple data centers, and you just shift traffic when something happens. And so your RTO goes very low because all you have to do is redirect traffic. Your RPO is the same as your replication with cold copy, same strategy there. And your app impact is similar. But then your cost is going to be the highest because now you have to have your application running in 2 different data centers full time. And that needs to, that's going to cost. So you have to think about which one actually works best for, or which one you actually need, and then trade off the costs. So then you might say, hey, if I have replication, then I don't need backup and restore. And that's not necessarily true. So replication is great for uptime, it reduces your RPO, but you've got things like, say you have a bug that's corrupting data in your database. Well, a replication strategy will very happily replicate that corrupted data across to the other side. And how do you get back to an uncorrupted copy? Same's true for ransomware. There you really want to have immutable copies because once your data is corrupted or encrypted so you can't access it and it's encrypted that way everywhere, you're in trouble. There, of course, are the trade-offs of costs. And so you really have to understand what your business requirements are going to be to justify your costs and pick or include both strategies. Now, for backup, we have some different terms for consistency. So a crash-consistent backup is one that's essentially the server crashed or you pulled the power on it. So everything that was written to persistent storage is there into the backup. And then when you recover, you're going to have to go through the usual recovery process. So FSCK or the database recovery or what have you. There's a possibility you may lose some data during the repair, but you should at least be able to get back to running system. Because if your application can't survive a crash, well, you probably need to work on that. And we can use snapshots without much impact on execution because we don't actually quiesce the application in this case. So then we may go to a fully consistent strategy where we actually quiesce the OS and the application, make sure all the caches are flushed, and so everything on the persistent storage is actually consistent. And so then when we restore, that's essentially like a clean boot. So there's no need to do a repair, nothing should be lost. But you may have your application unavailable while it's quiesced during the backup. Then another strategy is being actually application consistent, where your application or pieces of your application are part of the backup process. So one example of this might be PG dump with Postgres, where you can actually dump out everything consistently out of the database, and you can continue to use the database while the PG dump's running, because it's running in a transaction. And at the end, you have a fully consistent backup that you can then restore. So the impact of this is really going to depend on how the application does it and what you did there. Then inconsistent backups, we generally don't recommend those because on restore, there's a high probability that your restore may just not work or you may lose data. There's a few cases where this might be acceptable, like for example, if you're just backing up log files and you just want to have those available in case. And if you lose them, it's not a big deal. If you lose the latest one, it's not a big deal. But in general, not a great idea. So one of these other 3 consistency strategies is what you want to be doing. Now, one of the unique challenges in Kubernetes are operators. And operators are really great because they let you start to compose applications out of other applications. But since operators do things to modify your running Kubernetes state, then you have to start taking that into account during backup and restore or replication. So for example, if the operator is running and it's changing resources or creating resources in the middle of your backup, that may give you an inconsistent backup. You may have a PV that was created after the backup had already backed up all of the PVs or something like that. So one thing we'd like to see is adding options to operators to be able to quiesce them so that they don't make changes during backups. and then figuring out the relationship of the resources that are created to the resource that is controlling them. So for example, you create a Postgres operator resource, and then that creates a stateful set, creates some PVs, creates some PVCs, and you may say, okay, I just want to back up this one database based on the Postgres resource. In that case, being able to relate that resource to what was actually created is important. So many operators, we want to see operators doing a better job of relating things together. On restore, the order of restore often matters, especially if the operator is up and running. So for example, our Postgres example again, if we restore the Postgres resource first and the operator's running, then the operator looks and it says, oh, there's no stateful set, there's no PVs, let me create those. And it very happily creates an empty database for you. And as the restore continues on, it's like, oh, I need to restore these disks, oops, they're already here, and then the restore doesn't work. So what we want to do is we want to be able to do like a bottom-up restore, where we restore like the PVs first, then the stateful set for the operator that may be involved, and then finally the resource. And then the operator should look at this, reconcile, and go, oh, I don't have to do anything. So those are the kind of things, or being able to quiesce the operator during the backup. So these are the kind of things we want to work more with operators to get some better APIs for doing this, and just get awareness out there on this is what operators with stateful stuff need to be doing. Okay, so that's it for our white paper updates. We'd like to invite you to get involved in the data protection working group. We have a homepage here. We do meetings every 2 weeks, Wednesdays at 9 a.m., and the mailing list and a Slack channel. And with that, if you have any questions, we're happy to take them.